is ready. I hope that everybody came who can come, because competition is pretty strong. And first of all, some small organizational note from the organizers. If you want to ask question, you can do it under this address, and if we have time at the end, I'll try to answer that. But if we don't have, probably you can assume that I would answer, yes, this is very good question, let me Google it for you. Okay? Or, I don't know, let me check it for you. But anyway, let's see how much time will be left. So, let me introduce myself. My name is Maciek Próchniak. I came from Warsaw. I work for a small software company named Toke, and I'm doing, well, software development in various forms. Recently, mostly stream processing, Scala, and so on. And this is my project that I'm working on. It's called NoSQL. I won't be talking about it tomorrow, but still, I wanted to show you the logo. I'm going to talk about something completely different. And to begin with, I want to recall a memory of a project that I was working on about 6 or 7 years ago. I was a young developer, maybe not so young, but certainly not very experienced. And we tried to do a kind of ambitious project with all the latest toys that we could think of. That is event sourcing, CQRS, domain-driven design, sagas, some crazy, not really working NoSQL databases, and so on. And this project was quite challenging. We had a lot of difficulties. There was a lot of stress because, well, our relation with clients became pretty hard or harsh when some problems arose. But in the end, it ended up with moderate success. And what happens next? Well, I joined another project. This time, it was completely different one. This time, it was based on good old Spring. Good old Spring. There was no Spring Boot at the time, I think. So I felt like on holiday, because all I had to do was to put this magical annotation on the stuff that we wrote, and everything magically worked, right? No need to think about sagas, CQRS, and stuff. Of course, up to a certain point, up to certain requirements, because this is how our code looked like. And after a while, well, there came some particular requirement to handle some reservation of SIM cards. So what we had to do, we had to double into the gory details of this particular annotation. And what are the gory details of Spring Boots or any Spring annotations? Well, these are parameters. And what parameters do we have in transactional? Well, we have an isolation parameter. So what do we do? What is the correct value of this parameter? Well, of course, this is the correct value, and this is what is set by the default. So if you want to ask yourself, so what is the default's default, right? What is really like? Then Spring gives you the answer, okay, I don't care, just go ask your database. This will be the default, and I'm not to blame. So this is quite a reasonable explanation. And of course, it makes your code, well, not exactly portable across your database vendors. So we have to go a little bit further and ask, what are the possible values of ANSI isolation levels? And in fact, there are not so many of them. So the first ones just allow us to remain, to retain some basic sanity, right? This is just guarantees us that we won't read or write any garbage that database will allow us to, right? And these settings, especially the read committed, are pretty reasonable. And in fact, for many databases, this is the default isolation level. But unfortunately, it's not always enough. Because when we think about this kind of particular requirement like reservation, when we have one guy who's probably, I don't know, riding a train where the Wi-Fi is pretty low, and he says, okay, I want to make a reservation of some number from some pool, right, where they are free. We're in Oracle, so we have no Boolean type, but 0 1s. And there's this girl and he gets number 5. And there's this girl who's at home, so with good internet connection, also wants to make reservation, and updates this particular number. And the guy on the train with poor internet, he will handle update just now. And what happens with read committed level? Well, this bang. We don't have the consistency that we wanted to have, right? Some of our some of our constraints are not satisfied. So what can we do? Well, we can use some more kind of strict isolation levels, and ANSI level defines two of them. One is repeatable read, and the other one is serializable. Even the first of them, the repeatable read, is pretty strong and, well, in some cases can seriously degrade your performance, but the kind of holy grail of isolation is, of course, serializable isolation level. So let's look, what is the definition of serializable? In fact, if you dig deep enough in ANSI definitions, you can find two of them. One is this. This is kind of long, but if you read it, you may understand that, okay, transaction isolation level serializable means that we can pretend that the transactions were made by, well, essentially a single thread, right? We can pretend that database is single-threaded. It won't accept any beginning of new transactions unless the former transaction commits or aborts. Of course, in real life, it isn't handled that way because the performance will be kind of dramatic. But this is the definition. This is the definition by behavior. But if you look at the ANSI specification, you can see that there are also other definitions. And these definitions are in terms of certain phenomena. So isolation level is when some certain situation can or cannot occur. And for a serializable, ANSI defines it as serializable is repeatable read and prevention of so-called phantom reads. And it turns out that those definitions are almost, are almost compatible, but not quite. And only after a few years after defining all those isolation levels, people realized that there's a third notion called snapshot isolation. Probably we can connect it to things like multi-version concurrency control in databases such as Postgres, which says basically that each transaction can be thought of as performed by that the operations are performed by kind of private copy of the database. And it turns out that these single-threaded definition and these snapshot isolations are not really compatible, and there are certain subtle phenomena that, well, occur in snapshot isolation. Because let's think about the situation when we have family accounts. A husband has account, wife has account, and they can go below 0, provided that the sum of their accounts is above 0. So when husband wants to withdraw some money, wife wants to withdraw some money, then again, under snapshot isolation, it may very well happen that our environment is not satisfied. That is, under certain condition, of course, when the husband is traveling on train, well, essentially, they can go both under 0, right? So this may very well happen in snapshot isolation. And the interesting thing is that, for example, in Oracle database, still this is called serializable. So this may very well happen in Oracle, even if you run your transaction under serializable isolation level. So what do poor Oracle developers do? Anybody else? Yeah. Yeah, this is the way how you handle it in Oracle. So you kind of create additional artificial log so that such situations will be detected. Of course, at application level, you can handle this situation somewhat differently. That is by another annotation, by optimistic locking. Of course, not all these phenomena can be prevented by optimistic locking, but still we can get quite far with it. But what I want you to remember from all this discussion is that these ANSI isolation levels are by no means easy to understand. And this is kind of a screenshot from a project by Martin Kleppmann. It's called Hermitage. And he set up to discover what different subtle phenomena can happen in different databases under, well, kind of declared isolation levels. So you can see that it's by no means simple, right? There are a lot of exceptions, lots of asterisks, and, well, question marks. So if you happen to be in a situation when somewhere your gut feeling tells you that this is kind of tricky and subtle when it comes to isolation, concurrency control, and so on, I think it's good to go to this page and check how your database vendor will perform. And if he says that, okay, he or she says it's like repeatable read, isn't really repeatable read or something different? Is it serializable, or there are some guarantees that will not be achieved, right? Because in my humble opinion, even after 30 years after invented ANSI SQL standards, it's not so easy to understand all the quirks and subtleties of all of them. But fortunately, it's year 2019, and we don't have to worry, because we can do something different. We can use another annotation, and that is enable Mongo repositories. As it happens in Spring Boot, enabling this annotation causes us to enable different annotation, at least up to Spring 2.1, Spring Boot 2.1, I think. And this is the annotation that was up to recently enabled by enabling Mongo repositories. I wonder how many code bases suffer from not knowing such things and putting transactional annotations when they really won't work. But anyway, as we all remember, the creators of Mongo said, okay, once you have Mongo, you have document model, you don't need AC transactions. 80–90% of applications don't need multi-document transactions at all, and so on and so forth. Of course, there were some poor people who had, for example, designed banking applications and couldn't get away with it. By the way, this is a slide that's a few years old, from presentations of one of my friends. So this was the first slide, and the next slide was this. Challenge accepted, and my good old friend really did that. He implemented some banking application with Mongo and even got away with it. And now he's in the next room. He's Kuban Abdalik, but as you can probably see, he has a lot more gray hair than then. So it was not so easy. But years passed, and like 1 or 2 years ago, strange thing happened. And what did Mongo creators started to tell us? Wow, multi-document full ACID transactions are coming to Mongo this summer. I think it was last year. Yeah, it was last year. And with this final piece of puzzle, multi-document ACID transactions, the game is over, right? So once they implemented the functionality, they said, okay, this is really cool and needed functionality, which is kind of nice from marketing point of view. And if you look at the landscape after a few years from 2012 compared to what happens now, you will see that there are many, many vendors of databases, SQL, NoSQL, and whatever, that says, okay, CAP theorem is CAP theorem, but we can do now consistency, we can do transactionality, we can do SQL, whatever. Of course, probably not all of them live up to the expectations, and if you, I don't encourage you, but if you pass to the room where my friend Kuba is telling his story, you'll hear some horror stories about some of these databases. But nevertheless, I started to ask myself a question. Okay, so what happened? What happened in these last few years? What happened to CAP theorem? Was it broken or whatever, right? Because we've heard, okay, you can't have consistency and availability and so on and so forth. And that it was kind of mathematical, scientific theorem. So let's have a quick look what happened. And to start with that, we'll begin with the definition, right? And here lies the problem, right? This is the definition of the CAP theorem that I found on some random blog. And when you look at it, at first sight, it looks pretty reasonable. But if you think about it and you compare it to original formulation, you'll notice that it's not really the case. So let's look what Eric Brewer, the creator of CAP theorem, really said, and how is connection to kind of our reality. So the first definition is the partition. What is the partition? And it says, okay, we have to assume in our world that distributed system can lose arbitrarily many messages sent from one node to another. We just doesn't assume that there are some hackers who will tamper our communication. About the strong availability, this gets a bit more interesting because he says that, okay, to consider system available when it comes to my theorem, we have to say that each non-failing node has to answer. Not any node. each non-failing node has to answer. So this is kind of strong assumption. And about consistency, well, of course, this definition kind of complex. Basically, it says that as in ACID transactions, serializability meant that we can think of it as kind of single-threaded. Well, here the consistency, this is called sequential consistency, means we can think that we don't have distributed, that we can think of it as having only node. And please bear in mind that consistency in the language of distributed system and cap theorem is something completely different, or maybe not completely different, but different from the consistency from ACID transaction, when it meant, well, more like respecting foreign keys and so on and so forth. So once we have all these definitions in place, all this cap theorem loses its magic, right? Because when you have distributed database, well, you have to replicate stuff somehow, right? And if you have to replicate stuff somehow, you can do it synchronously or asynchronously. And if you do it synchronously, you lose availability. If you do it asynchronously, you lose consistency, right? So it's by no means very complex theorem, but just a corollary from these quite strong assumptions. So, now what? What's the real meaning of cap theorem? So the meaning is that it turned our attention to the trade-offs. That, okay, we cannot have anything, we have to sacrifice either availability or consistency. And even after a few years, many authors pointed out that these are not the only trade-offs that we have to make, right? That apart from consistency and availability, there is also kind of performance guarantees, and sometimes we have to trade throughput or latency, and what's more, these trade-offs can be different in different conditions, either when partitions occur or in normal our database working. And if you look, for example, at Mongo, similar things happen, right? So we can choose the guarantees when we perform writes. Either we don't wait for anything, or we wait until everything's written in some particular node. And if we read it, we also can read from any copy, and we can check from how many nodes we want to read to guarantee stronger consistency, and of course to sacrifice some availability or performance. But these are not the only trade-offs, because there's kind of a lot of, I would say, gray area between. And some people a few years ago researched that just a little bit and came up with the notion of high available transaction. The people were Bailey, Speckett, and so on. This is quite an interesting paper. And they said, okay, we know that we have to trade availability or consistency, but let's look, can we trade just a little bit of consistency and stay available? Or we can trade just a little bit consistent availability and still stay consistent, or the other way around. So at first we have these two notions. One is from cap theorem, the other one is from Bayes, just like Martin taught us in the morning, and they made up a few more definitions. One is linearizability, that is like sequential consistency, but also with the notion that the operations are ordered just like in real system time. And there are some kind of weaker guarantees. There's monotonic read writes, write follows reads, and these weaker definitions, it turns out they can be guaranteed in, well, available setting, right? So these are weaker consistency guarantees that we can have without sacrificing availability. But there are even more, right? There's even kind of more grayish area. This is why it's yellow. That's guarantees like read your writes or casual consistency. And they can become available once we assume that our client, that's we talk to only one node of our distributed database, right? If you lose it, well, we lose the guarantee. So it's more like, I would say, guarantees connected with certain notion of session, where we have few operations that we want to behave in kind of consistent way. This is the notion of causal consistency. And it turns out that, yeah, These are not just resets definitions because, for example, in MongoDB from 3.4 or 6, I don't remember, there's notion of session, and provided that our client uses kind of single-threaded ID, there are some additional assumptions and so on, we can use kind of session guarantees where we start the session, perform some operations, and until the end of the session, Mongo guarantees that certain phenomena related to consistency won't occur. When we think about it, we start to see, okay, we start the session, we perform operations, then we end session. This looks like more or less like transactions. What about transaction? Where are they? But the session doesn't have any transactional guarantees such as atomicity and so on. So we can look at this tree of different consistency levels and draw another tree of isolation levels connected to kind of more transactional operations working on few operations and see do they somehow relate to each other. And it turns out that they don't really relate to each other. To have both of the worlds, we have another notion of strict serializability. This is very, very kind of strict and strong guarantee, and this basically means we have everything. But in many databases such as Mongo, in fact, by tuning various settings such as read or write, consistency levels, and transactions, we can be in almost any place of this tree, right? And in fact, if you go deep enough in Mongo documentation, you can find such thing. It's not so easy to read and to comprehend, but if you read it thoroughly, you can see that it tells us under which settings, where are we here. And under consistency, under transactional operations. So, yeah. So at the end, Mongo really has some transactional operations that puts us somewhere here in the consistency guarantees. But if we look at the history of press releases, we can see that about a year ago or more, Mongo started to support multi-document transactions, but only if the database wasn't sharded. So in fact, it was like when we have the database that was small enough so that one replica would fit on one node, we can do multi-document transactions. But only recently, like 2 or 3 months ago, they managed to do it for sharded cluster, meaning that this is really fully distributed database and different shards can be on different machines, and so-called primary replicas can also be on different nodes. So what happened that they needed more than a year to do this? Well, essentially, the thing they wanted to do put us into kind of difficult place, because when they went from single-sharded transactions to multi-shard transaction, what they really wanted to achieve was distributed transactions, right? Spanning multiple nodes. When you have transaction that spans only one kind of primary replica, it's by some means, it's more like, I would say, still not really distributed transaction. But for multiple shard transactions, you have different problems. And how do you deal with distributed transactions? Well, it's kind of difficult. Probably most of you were in the lecture of Martin this morning, so you know that it's not a piece of cake. And the thing that we have to do is probably employ some form of two-phase commit, right? And if you look closely at Mongo blogs or documentations, you'll notice that this is exactly what they do, right? That for distributed transactions spanning multiple shards, they employ some kind of two-phase commit. Well, and this is probably where you start to wonder. So what happened, right? Are we back to square one, to our glorious enterprise landscape where we have two-phase commits, XA transaction managers spanning FTFMQ, PostgreSQL, and Oracle? Or what happened? Are we still in the land of microservices and WebScale, or where are we? Because, as a matter of fact, these XA transaction managers and two-phase commits, sometimes they used to work. I remember I had some situations when we employed such setting, and it worked, provided that we used only one server room controlled by us, and I would say, the throughput was no more than few requests per minute. But in different settings, kind of web scale settings, this probably applies. This is well-known statement by Pat Halland, retweeted by a colleague, Jonas Bonner, saying, okay, so two-phase commit is kind of like anti-availability protocol. When you employ two-phase commit, everything breaks. So what happens and why is that? Well, again, let's look why two-phase commit is problematic, why it breaks. So the two-phase commit looks more or less like this. So we have this coordinator like transaction manager. We have two systems and we have to assure that they agree on some fact. In this case, that the transaction either commits or aborts. So coordinator, what does he do when we want to commit some such distributed transaction? He says, okay, go system, I want you to prepare to commit the transaction. Are you ready? And the system says, okay, I'm ready, okay, I'm ready. And then coordinator says, okay, everybody's ready. That means we're really, really performing the transactions. Perform. And they're saying, okay, I'm performing, and finally, it's okay, we can proceed. So there are two problems, right? One problem is, as you can see, it's quite chatty protocol. We have exchanged quite a few messages to reach some agreement. But the bigger problem is that, yeah, it's really not available, because when coordinator dies at this point, it means no one can proceed, right? Because they already said, okay, I will commit, so they can't just abort. They have to hold their logs, and well, when coordinator is dead, who will tell them not to do it? Well, I know who will do it. It's the grumpy DBA, who will say, okay, you stupid programmers, I always have to clean for you, and he'll remove the distributed logs from the Oracle. But of course, it's not scalable because it's harder and harder to find grumpy DBAs. So, when two-phase commit is not enough, what can we do? We can have, of course, three-phase commit, which is slightly better because it apparently doesn't block, but still it requires even more communication, so the impact on performance and latency is kind of really, really considerable. And then there are also other consensus protocols like Paxos and Drafts, but they work kind of better, but they still have some problems. Like, for example, I think nobody can safely, except for creator Les Lamper, can claim that he understands Paxos, and Draft is a bit kind of maybe more simple, but still it has its quirks. So, with all these problems, all these protocols, what can we do with our distributed transactions, distributed systems? And as far as I can see in the kind of IT world, we can split our distributed transactions, distributed systems to kind of two groups. And one of them is kind of heterogeneous transactions. This is the case with microservices. We have many, many different services that are shared just by APIs. They can be written by different people, live on different plants, and so on, and they have to communicate. And in that case, I think that the agreement is mostly not to use such distributed availability protocols, coordination protocols, and use stuff like good old, at least once delivery and idempotence, or sagas, just as Martin lent us in the morning, probably using the CLRI API and so on, or some more fancy stuff like conflict replicated data types, right? So we leave that because we've been already taught about that in the morning. But the situation is a little bit different when we come to homogeneous system. Homogeneous systems such as distributed database, right? Okay, it's a distributed system, it lives on different nodes, but still we can have some more knowledge, better protocols of communicating with each other, because this is essentially one system, just geo-replicated, more or less geo-replicated. And this is the point where kind of we enter the domain of, I would say, brave NoSQL, right? This is the realm of all these fancy new SQL or not SQL databases. And we, of course, don't have time to go through the gory details how they are implemented, but I want to point you to two examples to see how people come up with ideas, how to solve those problems. And the first one is one of the, I think, older such databases, that is Spanner, that was kind of used to be proprietary system in Google for quite a few years, and only like a year or two ago it was made available on Google Public Cloud. And this is the claim that creators of Spanner brought us. And they said, okay, we know that everybody's saying that general two-phase commit is too expensive, the performers, because of performance degradation and so on. But we think that the developers are so stupid that it's better to say, okay, use this serializable, consistent database, and please don't handle eventual consistency because you'll break stuff. And if some performance problems arise, well, we can handle it somehow. So this is kind of bold claim, but well, many people believe that because it came from Google and so on. So let's look how this, from kind of 10,000 feet perspective, how this Spanner works. Again, it's replicated database, and of course it's sharded database because no hard disk will manage to contain all those data. And what about consistency? Well, when Spanner wants to write some data, that's one operation. In fact, it made so via some distributed consensus protocol. I think it's Paxos, so that each write is consistent kind of by design. Of course, they lose some availability, but we'll get to that, right? So each write goes to one particular replicated shard is done by some kind of Paxos algorithm, which makes it consistent. And if you want to make transaction spanning multiple operations, well, some ad hoc kind of transaction coordinator is created, more or less. And again, there's Paxos algorithm that steers this whole transactional process. So this is quite complex, probably really difficult to implement well. They trade off some availability because essentially this is not available system in CAP theorem sense, but we will get to that. But they do gain pretty strong guarantees. And there's additional secret sauce, Google's secret sauce on top of that. And that comes from the fact that Google owns their own server rooms, so they can come up with kind of proprietary API that's called TrueTime, which is based on additional hardware installed in their server rooms, like atomic clocks, GPSs, and so on. And what they achieve is that they can have consistent notion of real time on each node, even spanning different server rooms, regions, or zones, right? So what they achieve is this holy grail of strict serializability. So not only are the transactions kind of isolated, consistent, serializable, but everything is done with regards to the notion of real system time. So this is pretty interesting, but this is really complex setup. And what's more, well, sometimes there can be performance degradation, latency problems. For example, I believe that Google won't let you install a cluster of such database spanning, I don't know, many continents, right? So I'm from Asia to Brazil, which in theory would be possible, but due to the fact that each write is consistent, that would be prohibitively expensive in terms of latency. So some people said, okay, we'll take this design and implement it ourselves, and there are a few databases like Cockroach or something that try to do it. But other people said, okay, but maybe we can get rid of this two-phase commit protocol and this or another form altogether. Because, well, why in Google setup this works? And this is a claim, again, from creator of CAP theorem, who works for Google, so he may be a little bit biased. But he says that the availability of this Google database is so high that we can say, okay, it's almost available, so we can say it's consistent and available effectively. What does it mean effectively? And he proceeds to say, okay, it means that there can be some network partitions. They will be rare, but if they do occur, it will happen in such a situation, such big I don't know, problems that that probably your website won't work. And if your website doesn't work, who cares? Your client can't access your application. Who cares if database is ready or not? So this is kind of effectively available in their definition. So this is kind of interesting claim. But what can we do when we don't have, I don't know, geo-replicated server rooms with spare cables and whatnot? And there's also a few databases that try different approach. One is interesting one, although not widely known, is FaunaDB. That is based on so-called Kelvin paper. It's again a few years ago. It was a few years old. And what is interesting for me as Scala developer is that I see it's kind of based on similar ideas that come from functional programming. So idea is that again, we can have transactions spanning multiple operations, but when client wants to perform transaction, he doesn't do so in kind of imperative way, such as we used to, that we are used to. So begin transaction, sleep a bit, perform read, perform write, sleep another bit of time, and after that commit. The transaction is kind of declarative. I want to perform those 2 reads, and based on that, those 3 writes, right? Just do it. And then what happens when clients issue some such request, it is sent to, well, kind of distributed central transaction log that writes it to kind of global transaction log, well, atomically, consistently, and so on. So this is the part where there is some notion of coordination, but in fact, no real actual read or writes are performed. We just acknowledge that this transaction will happen in this amount of time at this position in transaction log. And after a while, the transactions are batched in few milliseconds batches, and then they are sent as kind of transaction inputs to all the nodes that store, well, that store actual data. And they perform the operations in kind of replicated way. But the trick is here that because we replicate this transaction input, we can we can perform the operation in deterministic way, right? So on each node, the effects of doing this operation will be the same. It may happen later, sooner or later. Some nodes may be currently broken, but after a while, they will be back, and everything will be again in consistent shape. So there are also many nitty-gritty details that we won't go into, but this is interesting because for me it's interesting because it's more like functional programming. So we have declarative transaction instead of imperative ones. We split the definition from the execution so that we can have deterministic order, and of course we have to acknowledge some limitations like no side effects performed in transactions, but we can get quite nice performance, quite good guarantees, and well, deterministic execution. So we've talked a bit about more or less esoteric databases, about some research stuff going on. We've talked about DACIT. Now we're heading to the end of this presentation, so let me get back to some more down-to-earth stuff. And we'll leave this distributed essential databases, and we'll move to the notion of transaction in messaging systems, right? Because these were like, so far we talked about many things that's work in progress. We'll see where it goes. Now we'll talk a bit about messaging systems, and in particular Kafka, that's kind of becoming the de facto messaging system for many users. Probably most of you know what is Kafka and how does it work. But just to remind you, it's not a JMS system, a message broker that we are used to from from the good old enterprise days. Kafka is more like distributed log, so that each producer writes to kind of distributed log file line by line, append only, and this is all the Kafka broker do. And then the consumers read from this distributed log file line by line as fast as they want, as fast as they can, and they are to decide from which point of this log file they want to read, right? It's by no means the job of the broker, right? He doesn't care where the clients are in the replicated log. This allows quite nice scalability features and good performance, but it moves us quite a long way from this setup that many of us are used to. That is, we have something like, I don't know, JMS ActiveMQ message broker. We have Oracle database, and we employ some XA transactions to achieve something like exactly once guarantee. So only after committing transaction to Oracle, we can assume that the message was consumed for the broker. So how can we achieve this in Kafka settings? Well, essentially, there are quite a few use cases that they try to solve. One is we have some messages in our Kafka topic, and we want to process them and write somewhere else, like database or microservice or whatever. The another use case is when you have one Kafka topic, we want to process data and write to another Kafka topic. This is mostly what, for example, Kafka streams do. And another is ingestion of data from some different place, like distributed file system, database, or whatever, process it and write to Kafka. So for quite a few years, it was not really possible. In Kafka, we had to resort to things like at least once delivery, idempotency, and stuff like that. But a few, I think more or less 2 years ago, the creators of Kafka said, okay, we have enough enterprise clients, let's try to add transactions to our distributed log. So what can you do when all you have is distributed log files? Well, you create transaction coordinator, and what do you put inside? Well, another Kafka topic. This is kind of like technical one. And then you say, okay, in the normal topics, there won't be only kind of normal messages, but some markers that allows us to detect where transaction started, when it stopped. The transaction can span multiple partitions, multiple topics, so it's kind of distributed because they can be on different nodes. And again, the fact that transaction started or aborted is written to this transaction, one single transaction log. And when consumers are consuming from the topic that to take part in transactions, they can say, okay, I want to read only committed stuff. So then, if they encounter a marker saying that transaction begins here, they won't read until the transaction ends. And what is also interesting is that there's a guarantee of atomic producer, so that when we write a few messages to different partitions and we commit it, well, it's atomic, right? Either all messages are written or no one, or none of them. So we have atomic producer, we have isolation level for consumers that is kind of read committed, and one not such nice feature is that consumer can be blocked by running transactions, because still we have to assume that consumer writes messages one by one, and it means that if some transaction is blocked, then the consumer can also be blocked. So we have to be careful about that. So how can we achieve something like exactly once deliveries in such settings? So let's take first the simple case when we want to read from Kafka topic and write to Kafka topic, right? And process it somewhere. So we are reading, we are writing, and we want to be sure that we acknowledge that is commit the offset that we've read, this one, only after when we successfully produced the messages to another topic. So here's the trick, because in normal settings, the consumer writes his position in the log, how many messages did he read. Well, where can he do this? of course, in another Kafka topic. So here, we can apply this atomic guarantees for different partitions, because the transaction essentially spans, well, the topics that we are writing to, that's kind of business topics, and the topic with offsets, right? So here we achieve this exactly once guarantee. And this allows us to say that Kafka is kind of effectively exactly once when we don't leave its own kind of, I would say, failure domain, right? But what about the cases when, for example, we want to read from the database and write to Kafka? Well, it turns out we can also solve this problem pretty easily, because more often than not, when we do such incremental ingestion, we just have to write the position of the last record that we imported from the database somewhere. And where can we write it? Of course, in the auxiliary Kafka topic, right? And we can do it atomically. So again, we achieve this exactly once guarantees, transaction atomicity. And in the other case, when we want to export something to the database, it's the other way around, because if on the other side we have kind of relational or transactional database, we can, that supports transactions, we can write in one transaction both the records that we ingested from Kafka, and, well, in some auxiliary table, we can write the offset of the last messages that we wanted to consume. So we leave the Kafka as failure domain, and we write everything in our, for example, relational transactional database. But for the generic case, when on the other side we have something like microservices and so on, probably it's not so easy, it's not possible, and we have to resort to, well, good old at least once delivery and some kind of idempotence, because we've left our safe homogeneous system and we have to resort to different ways to exactly once delivery. Okay, so to sum up, Kafka allows us to have atomicity guarantees when it comes to transactions. It allows us to, well, more or less reach effectively exactly once. But the isolation levels, if you think about it, they are pretty weak, right? It's only read committed. And for kind of more stronger isolation levels spanning multiple Kafka partitions, it's pretty, I think, difficult subjects. There are some things going on, for example, with the community of Apache Flink, how to do this, but it's still, I think it's still not really solved problem. Okay, so time's almost up. We've talked about, well, from different angles, about many different things. So what I want you to remember is first, yeah, that even ACID transaction can hide many mysteries, even when we have normal relational SQL databases. So take care and read documentation, because in the documentation there is also kind of difficult to split marketing bullshit from the real truth. The truth is there, but you always have to try to translate what they say to some kind of general definitions to be able to compare what are the real guarantees, what do they promise us, and what we have to take care of ourselves. And the last thing is, not only last things, almost last thing is that laws of nature probably do not change. Like the speed of light will remain in, like, for next few years, because in Spring 12 probably there will be some annotation to adjust that. But still, from time to time, it's good to look at the trade-offs that we are making, that we are used to make, because maybe something will change. The advance of different software techniques, the advance of hardware, that may make some of our trade-offs not worthwhile as it used to be. Right, if you're interested in such cases, I highly recommend this book. It's really great read, and yeah, it's really great stuff. And additional resources are one is Epson.io, which tests different distributed databases, and another is blog by Daniel Abadi, who writes about, well, again, isolation, transactions, and so on, in very nice, informative way. And that's more or less all. Thank you very much, and hope you'll enjoy the rest of the conference. I don't know if you have time for questions, but if you want, you can ask anyway.